Hi, welcome back to SelfCAD. You're watching part 9 of our 3D Modeling 101 series. So far, we've focused on creating different objects from scratch and taught you how to avoid some of the most common issues in 3D design. In this episode, we'll switch things up a bit and teach you how to import and work with 3D objects downloaded from the internet. This is an important skill to have as it will help you create more complex and detailed 3D models without having to start from scratch. We'll start by importing an object and show you how to examine it for potential topology issues. Then we'll explain how to solve them, and finally, how to modify the object itself. Let's begin. How to import an STL file in SelfCAD. SelfCAD supports a variety of file formats for both import and export, ranging from simple mesh formats such as STL and OBJ to mesh plus material file formats such as GLTF and GLB. For the purpose of this video, we'll use the most popular 3D object used for 3D printing, the 3D Benchy, found on the most popular geometry sharing website, Thingiverse. We'll start by downloading the object in the STL format, which is the most commonly used format for mesh-only file sharing. Now that we have the object, we can add it to our workspace. To import a 3D object, all you need to do is drag and drop the 3D file from your Downloads folder into the SelfCAD editor, or use the import function and select the object from your hard drive, and that's it. You'll notice right away that the object is rotated to the side. That's because the object has been designed using the z-axis for height, while SelfCAD uses the y-axis to describe it by default. We can fix this by simply rotating the object by 90 degrees on the x-axis, or changing the default orientation in the app settings so that you won't have to rotate the object after importing it. We will also upscale the object so it's easier to work with. We'll use the Keep Proportion option from the advanced settings so that we do not deform the object. And now that the object is ready, let's see if it has any issues. Examining the 3D object. It is imperative to inspect the object after importing it to find and fix any flaws that could complicate the editing process, and in some cases even cause problems with 3D printing. The most common issues we find in imported objects are holes in the topology, flipped faces, also known as flipped normals, interfaces, self-intersecting faces. Holes in the topology. Before we check for any holes in the topology, let me explain the issue first. Holes are a problem because 3D objects need to have a closed volume, also known as manifold or watertight. Any hole in the topology will make it lose its volume, making it impossible to use some editing tools. In a simple 3D object, holes are obvious, and you can spot them just by zooming in and looking at the object from all angles. However, the more complex the object is, the harder it will be to see if anything is missing. The solution to this problem is to assign a different color to the inside of the object to easily spot the holes. But before we do so, let me explain the theory behind it. What are inside faces? Digital objects have the concept of inside and outside faces, determining the inside and the outside of the object. And what determines what direction is what we call face normal, which you can visualize as a vector pointing from the inside to the outside of each face. And naturally, we don't want any inside faces to point outwards. You will not see any difference between the inside and outside faces in the default display, as they all have the same color. But you can easily spot them by enabling the back face coloring display mode, which will change the color of the inside faces, which you can change in settings if you want. Now you can scan the object to search for any discoloration. If everything is fine with the object, there will be no changes on the outside. But you can zoom into the object to see alternative color on the inside. You will see the same difference if you decide to split the object in half and don't add any volume. As mentioned previously, it also makes for a great tool for searching for holes. If you inspect such objects with enabled back face coloring, you will easily spot places that flash a different color from the inside, indicating that you have a hole in the topology. What are flipped faces? The second problem we can search for with back face coloring are flipped faces. When we talk about flipped faces, we're talking about a situation where the face normal, or the vector, flips and the inside face points outward. We can similarly spot such issues by inspecting the object from all sides like we did when searching for holes. But in this case, we're not looking for a changed color inside the object, and instead are looking for a changed color on the object's surface. Flipped normals are not just technical details needed for the rendering process. Because of flipped normals, the software might think the object has no volume, which is especially problematic for Stitch and Scoop or other tools that work with volume. How to fix holes. Fixing holes is simple. We have two different tools for that purpose, the Fill Polygons and Edit Details. Fill Polygons is the easier solution of the two, and it's always best to start with it. But if the object has too many missing faces, it may not be enough. In such cases, we can give more specific directions to fill the missing faces with the Edit Details tool, where we can use the Add Face mode to draw the missing face. Alternatively, if you want to keep the shape open, you can use the Add Thickness tool to add volume to the object and make it hollow. How to fix flipped normals. Flipped normals is an excellent tool for fixing the most common issues with incorrect face orientation, often caused by some 3D modeling tools that incorrectly assign the normals. On the first try, it will align all faces in a continuous flow. And once they are aligned, the second use of flipped normals will flip the entire geometry inside out, and on the next one, restore it again. You might ask, why should I want to flip the entire geometry? It's a good question, and we'll come back to it later and show you a practical use for it. But for now, let us go back to the problem with non-manifolds. Flipping non-manifold geometry. As I said, the most common flipped normals issues result from more complex modeling processes. For example, if you use fill polygons to close a complex shape, or multiple holes at the same time, it can often set some face directions incorrectly, which you can fix with flip normals. However, if the object has other non-manifold issues, they will prevent the tool from restoring the correct orientation. And the attempt to do so will result in the tool showing you a non-manifold alert. Flipping non-manifold objects. The solution to that is to fix them manually by selecting the flipped faces first and only then using the Flip Normals tool. This way, you will circumvent the manifold requirement when using the Flip Normals on the entire object. However, correcting and fixing the face orientation is just the start, as non-manifold objects often have other issues that require fixing, which brings us to the next issue we need to check for. Checking for inner faces. Inner faces are a problem because they disrupt the volume of the object, which should be completely empty from the inside. Interestingly, the Flip Normals and back face coloring tools can also help solve this problem. But there's one more tool that can help us solve this particular issue that we want to introduce: the back face culling. Back face culling uses the same logic as back face coloring, but it hides them instead of giving a different color to the inside faces. And because we can see the inside of the model directly, we can detect some of the problems we discussed earlier, and also find any inside faces that disrupt the volume. Using this tool is really simple. First, we flip the outside faces, and then we turn on the back face culling to hide them to inspect the inside of the mesh. And if you see any inside faces, you can simply select and delete them. And when you're done, you can simply flip the topology back into its correct orientation. Using the X-ray method. The previous method works great when you can find and select all the inside faces. But sometimes there are too many of them, or they're too small to easily spot them. In such cases, you can use the X-ray method to help you remove them. First, you need to enable the wireframe display mode and select all the faces. Then switch back to the solid display and use the Control key to deselect all the visible faces and use Delete. This way, you will remove all the inside faces we selected back in the wireframe mode. Self-intersecting faces. The simplest definition of self-intersection is where one face goes through another. To illustrate this, let's say you take a cylinder, scale it up at the top, and then hollow it. The best way to do this is to simply delete the top and use the Add Thickness tool as we've shown before, but to illustrate this point, we'll do this manually. We'll start with creating an inset in the top polygon, and then simply move it down. It will make it hollow, but because the top polygon was bigger than the bottom one, the faces will self-intersect at some point. In this case, the solution is to simply calculate what thickness is needed at that location, and scale it down accordingly to get an even thickness. But if you only care about visuals, you can simply use the back face coloring and scale the inset until it's no longer self-intersecting. However, there are more complex self-intersection examples where scaling is not a solution. For example, if an entire section of the object pushes through another, the best solution is to rebuild the object with the Magic Fix tool. It's the final option when all others fail. Other non-manifold issues. There are other issues such as duplicate vertices. They are less common than the previously discussed problems, but you will still run into them from time to time. We have already discussed the solution to this problem in the previous parts, and you can fix them with the Geom Clean tool to remove such vertices. And now that we've discussed all those problems, let's apply what we just learned in practice using the 3D Benchy we imported at the start of this video. Testing the 3D Benchy. Let's begin by enabling the back face coloring mode and visually inspect the object. You can notice some different colors at the edges, but that's just a rendering effect, and it has no effect on the overall orientation. Other than that, there are no differences in color, meaning that all faces are oriented correctly. Next, we'll use the Flip Normals tool to see if there are other non-manifold issues. The operation was completed without problems, meaning that the object does not have any major issues. So we can use the Flip tool one more time to restore the correct orientation and move on to the editing process. The editing process. There are a few things I've noticed during our visual inspection that I would like to improve on in this video. Simplify the mesh, remove the watermark, add our own watermark, and add nice coloring. Simplifying a mesh. Organic designs often require having a lot of polygons to express all the fine details, but often you end up with extra details that don't add any value, mostly as a result of tools adding too many polygons. The solution to that is low poly modeling, a well-sought-after skill in all 3D-related industries that focuses on creating nice-looking geometry from scratch. But when we import the object, we have to work with what we have. For that, we have created the Simplify Object tool, allowing us to reduce the overall poly count without deforming the object. Still, you have to be careful and test if the object stays manifold. Simplifying objects with sharp details, such as watermarks, can make these edges start self-intersecting, so you need to pay attention and don't simplify it too much. We will remove the watermark anyway, so we don't have to worry about it, but if you need to keep the watermark, you can temporarily remove it and add it back up after simplifying. Now, let's see how to do this. Removing watermarks. We'll start by enabling the Smooth Display mode. It will magnify the sharp edges and make the watermark much easier to see. The effect visually resembles that of the Round Object tool, but here it's just a visual effect with no impact on the overall geometry. So now that we see the problem, we can approach it in two ways. The first option is to plaster the object and just smooth out the watermark until you can't discern it from the surface. You can do that with the Smooth and Flatten brushes from our Sculpting tool. But it's not ideal. Sculpting is best suited for organic designs and doesn't work well with sharp edges. The second and preferred option is to delete the section with the watermark and replace it later on. With this option, you must be very precise with selection, which is not easy when working with objects with hundreds of thousands of faces. In such cases, basic selection tools like polygon selection, tolerance, and marquee selection will not be of much help, simply because many small faces go into the object, making it difficult to select them. In this case, the best option is to use the cube selection tool, which allows us to make clean cuts in a single sweep. To make it as precise cut as we can, we'll start by measuring the height of the text by simply selecting one face and checking its position on the y-axis. As you can see, we get a 1.5 reading. So we'll make the cut at 2 just to add a little more space. Once we finalize it, we can use the split tool from Utilities to separate the pieces and then hide the upper part just to have more space to work with. Now we can switch to wireframe only mode and marquee select the polygon at the bottom along with the text and remove it. With that done, we can show the main mesh and use the Combine tool to merge both objects back together. And once it's done, we can simply use the Fill Polygons tool to close the Benchy at the bottom, leaving us with a perfectly smooth surface with no trace from a watermark. Now let's move on to the other watermark, where the problem is even more complex because it is at an angle. To account for that, we'll use the Cut with Plane tool, which operates similarly to cube selection, but offers a little more flexibility. Once we enable this tool, we need to enable the Split Objects option in the Advanced Settings to automatically split the object when we make the cut. Then we'll disable the bottom top plane and use the Draw Plane option to create a custom plane to create a cut. Now, when we rotate the camera, you'll see that the new plane is perpendicular to the surface. But before we make the cut, we have to offset the plane to accommodate the text inside of the object. As you remember, the text was positioned at 1.5 inside the object, so we'll offset it by 2 just to leave some extra space. Now we can finalize and start removing the watermark. Here, the surface on which the author added the watermark is not even because polygon selection highlights only small pieces. But we can easily overcome this problem by increasing the tolerance in the advanced settings to select the entire background. Once we remove this part, we can follow the same steps as before to select and delete the rest of the text. Then merge the pieces together and finally fill the hole in the object. And that's it! We've successfully removed the watermarks and kept the object manifold. And now that you know how to remove old watermarks, let's see how to add your own. Adding a watermark. To create and add a watermark, we need to create the text first. Position it in the right place, and then engrave it in the mesh. We'll add the watermark with Text Generator and position it on the object with the Snap tool, with the magnet option enabled in the advanced settings. This way the watermark will rotate just so it can snap flat to the surface. Now we'll just scale it so the objects intersect, change the color of the text for the watermark to be more visible, and engrave it using the difference from the Stitch and Scoop. This option works well when working with flat surfaces, but what about when you want to engrave a watermark on a rounded object? In such cases, we need to get a little creative. We'll start by creating a copy of the object, positioning the text where we need it, and using the intersection option from Stitch and Scoop to create a rounded surface for the watermark. Now we can move the text out of the object, using the difference option to round it on the other side, and finally engrave it in the object. Now let's color the object. Now we'll add some colors to the object, which interestingly also depends on selection. It's not difficult to change the color of selected pieces, but it is difficult to select those parts, especially when working with complex objects such as 3D Benchy. Thankfully, you can use all of our selection tools, some of which we highlighted earlier in this video, and others showcased in previous episodes, to select and deselect parts as needed. The problem, however, is that all those tools are limited to creating linear cuts and are not enough for artistic design. Thankfully, we also have an option for that in SelfCAD, similar to the lasso tool from Photoshop. We'll start with the 3D sketch and switch to the object mode, allowing us to draw a profile on the surface of the object. We'll draw a nonlinear profile around the Benchy, then go back to plane drawing and draw a small circle that we will sweep along the first profile with the Follow Path tool. As you can see, we didn't draw the original profile perfectly, but that was by design. Because of that, Follow Path created 2 objects instead of 1, making them non-manifold. But we can fix that with Magic Fix to rebuild those objects without those problems. Now we'll color this new mesh and make a copy of it. We'll use that copy to create an intersection with the Benchy with Stitch and Scoop and hide it. And then use the original object to cut out the difference from the Benchy. With that cut, we can now easily select the regions below and above the cut with polygon selection with increased tolerance and deep selection settings to change their color. And now that we created the cut and changed the colors above and below it, we can go back to the created intersection. Scale it up by just a fraction, just so it will intersect with the Benchy, and use Stitch and Scoop Union to patch up the engraving, leaving us with a smooth surface. Now we can enable the material selection, select this part, and change the color just so it blends seamlessly with the rest of the model. Exporting your 3D model. Now that we've finished the object, you might want to export it. In SelfCAD, this process is just as easy as importing. Just click on the File menu at the top left corner of the application, click Export, and select the file format in which you want to save the object. It's that simple. And that's it for this video. We've covered everything you need to know about inspecting and fixing any issues with imported objects, and showcased how to edit complex objects. And we hope you'll be able to use those techniques in your work. Make sure to hit like and subscribe. If you have any questions, feel free to leave comments below.